for it.
Okay. So um, basically in this talk, I would discuss what we have learned over the couple of years. And so basically, we started off as a research project, and what we wanted to see was how does Spark perform on the scale-up machines. And in this talk, I'm going to share what problems we found out and what are the solutions we tested. So actually, the first question is that why we should care about. And what we see that over the past couple of years, there is an exponential growth in data. And when we do look towards the technological side, we also see that the Moore's law is also going to end. And there is actually a growing technological gap between the two. And again, then we see that the current existing literature, it also tells us that these in-memory data analytics and the underlying hardware, they don't go along quite well. And also, then there is, let's say, new memory and promising technological solutions are also coming up. So the idea is that how we can, let's say, leverage the existing hardware in a better way, and also, let's say, how we can incorporate these novel memory solutions that are coming up in future. So what we see is that this kind of a war between the scale-out oriented frameworks and the scale-up frameworks. So on one hand, we see Spark, Flink, which have been designed to scale out to multiples of thousands of machines, whereas on the other hand, we have these scale-up frameworks that have been designed to actually scale up to 32 cores. But the question is that now, let's say, it's very common to have a dual socket servers from Intel. And what we want to achieve is to actually, let's say, narrow down this gap between these two worlds. And how we want to do is we want to do it in a very transparent way. And that's where we see that we want to do it through the hardware architecture support. So on the left-hand side, what we found out is that basically Spark has a very poor multi-core scalability, and we found out a certain number of problems with that one. And then on the right-hand side, that's the solutions we have proposed, and one by one, I'm going to go in that one. So what kind of methodology we adopted is this profiling methodology, where we first tune the internal parameters of Spark so that we get the best performance out of the applications. We tune the parameters of JVM. And then our most analysis was based on using these hardware performance counters, which are available inside the processors. And these are the benchmarks that we use, and you could see that our benchmarks, they cover almost all. It covers the whole domain, going from Spark Core to Spark SQL, GraphX, machine learning, and also stream processing as well. And that's our machine on which we conducted all our experiments. So you can see that it's a dual socket machine, and each machine has 12 cores, and with hyper-threading enabled, basically in total you have 48 hardware threads. And you could also see that each node has also 32 gig of memory as well. And that's the graph. On x-axis, we see the number of executor pool threads, and on y-axis, we have the speed up. And what we see that basically that the performance, it gets flattened out as we go beyond 12 threads. And next, we're going to see that what were the reasons we found out that why it was performing badly. And the first thing we found out that there is actually a thread level load imbalance. And if you look at towards the right side, we have actually all the executor threads, and on y-axis we have the elapsed time. And then we see this CPU time and the wait time corresponding to each thread. And when we look towards the right-hand side, we see that the thread number 24, 5, 6, and 7, I mean, you have less CPU time versus the ones which are the threads number 1, 2, and 3. And what we, let's say, hypothesize is that if let's say all these threads are taking almost an equal amount of CPU time, the overall elapsed time could be reduced. The next thing what we found out was that actually what is the impact of garbage collection? When we increase the number of threads, how much GC overhead do we get? And the graph on that side, we see that as we are increasing the number of cores, basically the time spent on the garbage collection is increasing. And let's say that graph is more focused where everything fits inside the memory, which means that the input data set is 6 gigabytes. And then on this side, we see that what happens when we are increasing the input data set. And we see that basically that the GC does not scale linearly, and there's an exponential increase in the GC overhead. And it means that basically GC has an adverse effect on the scalability of Spark applications. Next, again, what we saw that let's say how does the file I/O affect the performance? And here again we see basically the CPU time, the wait time of the file I/O, and other wait times. And we see at least for most of the workloads that as we are actually increasing the input data side, basically the wait time on the file I/O is actually increasing. And when we look towards these let's say percentages, there's an exponential increase. And for example, in the case of sort, when we are increasing the file size by 25x, the input data side is increased by 4x, whereas the fraction of file I/O increases by 25 times. So what it means is that basically still, let's say the file I/O is one of the performance bottlenecks as well. Here we see that on the graph on that side, we see that as we are actually increasing the number of threads, basically your work time inflation is actually increasing. And what does it mean by the work time inflation is that, for example, when you have a single thread and then you have 4 threads. So ideally, let's say the sum of the CPU time taken by the 4 threads should be the same as the one taken by the single thread. But we see that when we are increasing the number of threads, it actually takes the more amount of CPU time. So for example, here on this graph, when we are using these 24 threads and we add those CPU times together, so we have this additional overhead, which we call the work time inflation. And in the next graph, we would see that where does this work time inflation coming from? And here, the graph on the left, we see that actually, so this is the data which is focused more about, or that was taken from the hardware performance counters. And this graph, or let's say this data, it looks at where are the bottlenecks at the microarchitecture level. And what we can see that that most of the workloads, they are actually back-end bound. It means is that the stalls are mostly at the back end of the processor, where the execution units are and where the caches are as well. And then when we break down further, let's say this back-end bound stalls on this graph here, and we see that most of, let's say, these workloads, they are actually DRAM bound. So it means that most of the Spark workloads, they are constrained by the accesses, by the frequent accesses to the DRAM. And the other thing what we see is that most of these workloads, they are not using the caches properly, especially when we look towards the L3 bounds. So the L3 bounds are quite small, whereas the DRAM bounds are quite large. So it means that basically your last level caches are not being used properly. Another thing which you don't see in these graphs is the L2 bounds. So it means that actually that once you miss at the L1 cache, it goes directly either to the L3 cache or to the memory. So which means that these workloads, they're not using the L2 caches properly as well. Okay, so now here, up till now, the people at the Databricks, they also know that these workloads are DRAM bound, and they came up with the project Tungsten, and the idea was to come up with these cache-aware algorithms. So here we tested, let's say, how efficient these cache-aware algorithms are. And when we compare basically these data frames versus the RDDs, we could see actually this better instruction retirement in terms of data frames. And why is it so? Because in case of let's say these data frames, you have less DRAM bound stall cycles, you have less starvation of the execution resources, and also you are using less bandwidth. So basically, from where what you could see is that data frames or the Project Tungsten related optimizations, they do actually improve the performance of these applications. The next thing is that since we found out is that DRAM has that garbage collection is a performance bottleneck, and the question was that okay, most of the data scientists they are not quite expert in tuning the garbage collector. So the question was that is there any garbage collector which works well without much tuning efforts? And we found out is this parallel scavenge garbage collector. It performs better without out of the tuning, without any tuning effort, which means that out of the box solution of parallel scavenge is better than G1 GC garbage collector. Again, the other question was what we found out is that up till now, so if you have let's say 64 gigabyte of memory, and one way of doing the things is that you actually use one executor and you give all this 50 gig to that executor. So the first question, so here what we found out is that what happens if we, let's say, instead of using one executor, we use two executors, which means is that we keep the number of cores total constant, but let's say one or two executors. Basically, each executor uses 25 gigabyte of memory, and it is using 12 cores. And then when we go to 6 executors, so it means that let's say it is 24 divided by 6, and then it's again 50 divided by 6. And what we see here is that actually multiple executors they perform better instead of one executor. And the reason behind is that because let's say JVM has this compressed data oops optimization, which does not work beyond 32 gig. And that's why, let's say when we go from one executor to two executors, we see this performance improvement. And when we go beyond, we don't see much performance improvement. So what we propose from here is that you should use the executor's size, which is multiple of 32 gig. Another thing is that, okay, if the workloads are DRAM bound, and we have this, let's say, a dual socket machine. So the question is that would NUMA awareness would give performance improvement? So basically, what happens is that if you have the workload running on one socket and if it has to access from the remote memory, the latency of that access would be twice compared to the one which you get from the local memory. And here, let's say on the top of the graph, we see that actually for most of the workloads, it does not give you much of the performance gain. But when we look towards these graph analytics, you could see, let's say, 10% performance improvement. And the question is that why is it so? That has been explained in the graph over there, because in those workloads, we don't have many remote accesses, whereas in terms of graph analytics, we have more remote accesses. But again, the question is that, okay, why only 10% speed up and not much more? And the reason is because these workloads, they do not saturate this quick point interconnect bandwidth. And you could see that most of these workloads, they use around, let's say, 20 gigabytes per second. And whereas in these dual socket machines, we have 2 QPI links, and that's much below the limits of that one. The next thing is that hyperthreading would help, because generally if your workloads are DRAM bound, and if you have let's say multiple threads sharing the same core, you could actually hide the memory access latency. And in these graphs, what we are showing, especially the graph over here, that you can see that actually these local DRAM bounds are actually getting reduced for most of these workloads. And also, you could see that when we compare these bandwidth numbers, they also follow as the multicore execution. And again, here on the graph at the lower hand side, we also see that basically hyperthreading is actually effectiveness. So this is a parameter defined by Intel, but from where you could actually, so if the numbers are around 1, so it means that the hyperthreading is effective. So keep the hyperthreading on, I would say, for your machines. The other thing is that in Intel, we have actually a set of prefetchers, and there are two L1 prefetchers and two L2 prefetchers. And generally, prefetches, you could actually get 5 to 10% performance improvement if they are working fine. But if they are not working, and if they are polluting the cache, you're going to actually get the performance degradation. And in this graph, we actually tested how these different prefetchers actually perform. So we see that, basically this L1 DCU prefetchers, for most of these workloads, if you actually turn off those prefetchers, you can actually get almost 15% performance improvement. And why is it so? You could see here the graph over there that basically your L1 miss impact is improved, and your L2 hit rates are also improved. So it means is that you should actually disable the next line prefetchers, and that would actually result in these 15% performance gain. So. So up till now, what we have seen is that how you could actually tune. So you should keep your workloads NUMA aware. You should keep the hyperthreading on. You should turn off some of the prefetchers, and you should actually set up these executors so that they're not more than, or each executor does not consume more than 32 gig of heap. What's the other techniques? So one way of improving the latency is that instead of let's say bringing the data to the CPU cores, why don't we move the computation closer to the data? And that's what we are actually proposing and working right now, that we're actually proposing the hardware accelerators near the DRAM, and also the hardware accelerators near the storage device. And yeah, but the question is that, for example, should we go for the 3D stacked memories, or should we go for these normal DRAMs? And let's say actually here, what I'm trying to show is that the major benefit that you get from these high bandwidth memories is that if your workloads are saturating the memory, because then let's say if you're working in this exponential region, you're going to get this additional latency because you're saturating the bandwidth. So the first question is that do these workloads actually saturate the bandwidth? And what we see here on the graph at the top is that for most of these workloads, they actually do not saturate the available memory bandwidth. And in fact, let's say, I would say the performance improvement is also more or less the same when you actually reduce the DRAM frequency. So what does it mean is that that if the performance remains the same, reducing the DRAM frequency means that that basically you are actually improving the energy performance. And also on the graph down there, we see again this memory consumption over the period of execution, and then we see that okay, even if we have some spikes, but still they do not saturate the memory bandwidth. So then the next question is that okay, that if you have, let's say, these Spark workloads, the question is that what kind of these workloads would benefit from accelerators near the storage? What kind of workloads would benefit from the accelerators near the DRAM? And what we found out from these graphs is that actually most of these workloads, they also do not actually saturate the disk bandwidth as well. So it means that when we talk about that file I/O is the bottleneck, it's not let's say the bandwidth, but again it's the latency problem. And what it means is that how we can solve the latency problem again is that by moving the computation closer to the closer to the hard drive or closer to the SSDs. And on the graph on that side, we see that actually most of these Spark SQL workloads they are actually bound by the idle time, and then let's say there is more wait time on the I/O. Whereas for the other workloads like for example graph applications and stream processing applications, mostly let's say the CPU time is quite high and the wait time is quite low. So it means is that basically these Spark SQL workloads, they're going to benefit from near storage processing, whereas we envision that the rest of the workloads, especially graph and streaming, they're going to benefit from near DRAM accelerators, whereas when we come towards these machine learning applications, we actually see that here you have also more wait time on the I/O and also more CPU utilization. And there we actually propose a combination of both. So again, I'm going to skip this one. So that's what I have talked, and that's again my last slide here. That so we found out that okay, the poor multicore scalability of Spark is because of the work time inflation, because of thread level load imbalance, wait time on the I/O, and the GC overhead. And then we found out that okay, work time inflation is because of DRAM bound. And how we can solve the problem of DRAM bound is by bringing the NUMA awareness, by keeping the hyper-threaded cores, by not using the next time prefetches, and by lowering the DRAM speed. And in future, we are actually working in this area of this hybrid in-storage processing and near memory processing for these big data applications. So if you want to go deep and read further, these are the couple of papers which you can look at. And yeah, and that's my last slide.
All right, do we have any questions?
So you talked a bunch of techniques that will individually improve the performance when using one of them. And if you use them simultaneously, do the improvements stack up, or how does the...
Yeah, definitely. That's the whole idea. That, for example, when I'm talking about in the end this golden recipe that you should keep the prefetchers off, you should keep the hyperthreading on, and let's say instead of using one executor on a dual socket machine, use two executors, bind each of them to its own socket. Basically, all these improvements, they actually add up. Yeah.
Same exact question.
Yeah. Well, I don't. Let's say I don't have those combined numbers, but I would expect if you add them together, it should be somewhere around I would say 30% maybe.
First, I really enjoyed this. I'll follow up your references. Second, how do you disable prefetching, given it makes such a big difference? Can we do it in process, or is it kind of a boot time optional? Or do I put F10 on the BIOS at startup or something like that?
Let's say that I think until last year it was not. It was only possible to do through BIOS, but now Intel has released some information that there are actually some registers which you could through which you could actually disable those prefetchers. So it means that one of the things that we're also looking at is that how would this dynamic switching on and off of the prefetches gonna work, or how it can improve the performance. So yes, you can actually do that dynamically as well.
So you've run all these analysis for Spark in particular, and I think earlier today at the keynote speech we had the example of just a freshman writing some Java code. Have you done sort of benchmarks, say, in Spark versus just your plain old Java code?
So I couldn't get the question. So what was the question?
So I was just wondering if there's sort of let's call it a baseline that you can draw between Spark code and maybe freshman written Java code? Is there sort of a comparison there in terms of, because I'm trying to figure out what part of this can be attributed to Spark and which part of this is just JVM?
Yeah, so let's say that in one of the graphs I had actually compared this project tungsten related optimizations where they are actually using let's say off heap memory, and they're also using these cache aware algorithms, and that's where I actually showed that basically by using this off heap memory and by using let's say these cache aware algorithms, your instruction retirement is actually improved, and your let's say this DRAM bounded stalls, they also do decrease. So yes, let's say when you look towards these optimizations and when you look at the numbers, and they do correlate. Yeah.
Any other questions? All right, let's give one more round of applause.
Okay.